Today I will present you the stress concentration calculation of precipitate matrix interface during crypt deformation. So I will start with the context. The austenitic stainless steel, so 316Ln, that we use as one quantitative for so-called component of a nuclear power plant of generation 4, so-called also the sodium-coated fast reactor. And the in-service condition will be at high temperature of 550 degrees C for the long-term tensile stress. So that's why we call it crypt test we do here. And in-service duration could up to 60 years. But from what we know, for the moment we have the crypt experimental lifetime may reach 25 years, which come from NIMS Japan. That's why we needed to do the long-term crypt. We studied and simulated the long-term crypt damage to make correct lifetime prediction. The 316Ln that we use have grain size of 15 to 30 micrometer, and intergranular precipitation could be M2366, sigma phase, or T-fast, and the others. From this curve of the stress lifetime, we can observe the change of slope, which from short-term to long-term, which show us that the short-term crypt should consider as necking, which characterized by the local area reduction. For the long-term crypt, it will be intergranular cavitation damage. It is not such clear, but we have precipitate here along the grain boundary, and we observe the cavitation just on the interface of precipitate and grain boundary. I want to calculate the stress concentration of the interface. At first, I must to do some adjustment of the parameters. For the FCC structure, we have 12 slip systems. We use this equation to calculate the step rate. And we use the Taylor relationship to calculate the critical shear stress. There are already lots of parameters well known. It's shown here. As you have two parameters we want to specifically work for 316. This is volume activation and dislocation density. For dislocation density, we use the experimental result of the challenger. And we propose this equation, which is an adjusted equation to calculate the density dislocation in function of the stress, applied stress. And we will fit in the activation volume by the macroscopic crypt string curve. For that, we use this aggregate, which is a polycrystal aggregate, which have content of grain with random crystallographic orientations, for which we block at 6 degrees of freedom of helium body, and we apply the stress on two opposite faces. We studied the effect of number of grain and the number of elements per grain. So after that, we decided to use 6 cube grain and 7 cube infinite element per grain to do our simulations. By fitting from the experimental curve to our simulation curve, we found that the volume activation should be in order of 120 BQ. After this adjustment of parameters, we can do our calculations of stress concentration. From our SEM observations of the longitudinal section of specimens, we can observe that the precipitate along the grain boundary, the precipitate could be bean shaped or ellipsoidal. Some of them are circular. And we can observe just the cavities on the grain boundary, where we have the precipitate. And the shape factor of the precipitate is generally between 1 and 5. The majority is between 1 and 3. That's why we make this mesh to do our calculations, which has homogeneous matrix outside, which who is elastoviscoplastic using untreated law for the primary creep and the nominal for secondary creep. And we have two green inside, which have the different crystallographic orientation using our viscoplastic law. And finally, we have a inclusion inside, which is here, which is proposed to a linear isotopic elastic. The stress that we work on is the stress along the interface of inclusion. For that, we studied at first the size of the homogeneous matrix. It means that we take the size of homogeneous matrix 2.5 size of green to 12.5 size of green. And finally, we found that with 7.5 size of green, we can already find a quite good coherency compared to the 12.5 size of green. And for the report between the size of inclusion and the size of green is 7, which is correspond to our observation, which means that 3 micrometer precipitate in a 20 micrometer green. We start, of course, the effect of creep strain, which means that we found that maximum normal strain occurs at the strain reach 3.2 deformations and the creep time of 1,500 hours. That's why for the following we do a calculation until 4% deformation and 2,000 hours. To start our study, we start with the effect of young modulus of this inclusion. That we sampled it from 100 GPa to 400 GPa, but this parameter do not make significant influence on stress concentration. So that we take this value 350 GPa, which is young modulus of M13C6. And then we start the effect of random crystallographic orientation of Tuning-Berkeley. Here we have the black line, which corresponds to inclusion directly in the homogeneous matrix. And then which shows random couple of the orientations. We make simulation for 30 sets of the random couple. We observe clearly that this crystallographic orientation make a very strong heterogeneity in the interface normal stress. We characterize this effect as a ratio between the maximum normal stress in the homogeneous green compared to the maximum normal stress in the homogeneous matrix. We found the value of that. This ratio can be between 0.33 and 4.14, and the mean value will be the 1.85. And after that, we studied the effect of the shift factor. The shift factor will be from 1 to 10. We found that increasing the shift factor, the stress is increasing. It could maybe have a saturated after, but it's not have done for the moment. And for the moment, we find the maximum value of this effect could, from the factor 10 to 1, we find the maximum was 4.25. But this factor could be changed in function of the orientations. So most calculations are needed to characterize this effect. From our TDM observation, we can find different geometry of the precipitate, which means that we can find the pointed sharp and circular sharp, circular extremity. And we have the precipitate that we can find, which is symmetric compared to the green boundary, and some of them are just in one side of the green boundary. This allows us to continue our calculations. We compare the different form of the sharp from singular to this linear shape, we can find the record of 1.22. But this effect will be influenced by the shape factor and the round-down rotations. So the further studies are in progress. We studied also for the shaft, we have different angle. We studied from the 30 to 60 degree. For this point 1, we found that the stress will be decreased from 30 to 60. But for the other side, point 2, this point, we find this inversely decrease. And also, we studied the symmetric precipitate, compare the symmetric and asymmetric precipitate. We choose several different orientations to make the calculations. The ratio between the maximum normal stress of asymmetric precipitate to the symmetric precipitate could range from 0.5 to 3, and the mean value will be 1.5. But this result needs to be confirmed by experimental observations. It means it should be easier to find cavities on the precipitate in this form. Okay, we'll soon finish. It will be conclusion and work in progress. So the conclusion is that first, the variety is shown only due to the round-down orientations of the two neighbor grains. It could explain both the continuous and heterogeneous cavity nucleation. And taking into account the crystallographic orientations, the shape factor, the tip angle, the asymmetric inclusion, the finite element calculation of interface stress concentration could up to 40 times higher than the tensile stress. Such high local stress are close to the interface fracture stress of increasing interface based on atomistic consideration. For the work in progress is that there is one effect that we haven't done, is that effect of angle between the grain boundary plane and the tensile axis. And in the following, we want to use a cohesive zone model to simulate the fracture of interface. And finally, in our final objective, it will be a combination of the finite element calculation and experimental observations to calculate the cavity distribution and cavity nucleation rate during crypt deformation. Thank you for your attention.